So in this unit, we're going to focus completely on the nomenclature of organic compounds. And in order to start that unit and that information, we're going to start specifically with alkanes because they are the most basic organic compounds and will lay the foundation for all other types of nomenclature problems. So we've looked at alkanes when talking about degrees of unsaturation and functional groups before, but alkanes are hydrocarbons that have all single bonds, and they can be bonded in different ways. They can be bonded in a straight chain format where each carbon is connected to every other carbon sequentially, or they can be bonded in a branched format where carbons are bonded. There is one straight chain, but then there's sort of these groups or substituents coming off the side of that main chain. So we'll start with straight chain nomenclature specifically because it also applies to the branch nomenclature, which is more complicated. So the first step of naming something in a straight name nomenclature procedure is just counting the number of carbons in the molecule that you're shown. And so this was what makes a good understanding of skeletal or line bond structures really important. So in this example molecule down here, we have 6 carbons. The next step would be that however many carbons there are, that becomes the prefix of our name. And so there's a set of prefixes that you do need to know and start to commit to memory, mostly just up to 10. So meth being 1, F being 2, prop being 3, bute being 4, and then onwards up to 10. And so that becomes the prefix of our name. So because this straight chain molecule has 6 carbons, our prefix would be hex. And then lastly, you're going to add ane onto the end as a suffix to indicate that this is an alkane. So this molecule would be called hexane. And you could add that ane onto the end of any of these prefixes to get the corresponding molecule with that number of carbons. So methane, ethane, propane, these are actually really common gases and used in combustion and grills that you might have heard of before. And so this is where their nomenclature comes from. So straight chain nomenclature is pretty straightforward, and we're going to apply those same concepts to the more complicated branch structured molecules. So when looking at how to name a branched alkane, the first most important thing is to find the longest chain. And so this often messes people up. I tell people don't fall into the straight line trap. Sometimes that longest chain is not always in a straight line. So you really need to look at the molecule in depth and be able to identify what the longest chain is. That longest chain is called the parent chain, and if you have an example where there's 2 chains of the same length, you're going to pick the one that has the most branching, the most substituents on it. And then from there, you're going to place that parent chain at the end of the name. So if we look at this example molecule on the top, the parent chain here does happen to be horizontal, the straight line, 1, 2, 3, 4, 5, and based on the prefixes from the previous slide, that would mean that the end of our name would be pentane. And then I have to use additional steps in order to account for these groups that are hanging off the end of the chain. So our next step, there's a lot more for the branched alkanes, is those things hanging off the parent chain are called substituents. You've heard me talk about them before. And you're going to number the chain so that the substituents get the lowest possible combination of numbers. Okay, so for example, if I look at this chain down here, on the last slide, you saw me number it this way. But it's also just as feasible for me to number it starting on the right. And so the question is, which gives me the lowest possible combination of substituent numbers? So here's the numbers that could be for one substituent, and here's the number for the other. So this clearly shows us that the blue would be the correct numbering because the substituents get a combined number of 2 and 3 as opposed to 3 and 4 for the green numbering system. If 2 numbering systems come out the same, then you're going to start looking at priorities of substituents. So this is only if the 2 numbering systems are the same. First priority, lowest possible numbers. From there, if they are the same, you're going to give the halides, so any halogens, bromine, chlorine, iodine, fluorine, lower numbers than any carbons that are hanging off the chain. That's what alkyl groups are. And then if they're still equal, you're going to use the alphabet for those alkyl groups. So if it's earlier in the alphabet, starting with an A, B, and C as opposed to an elemental P, those would have priority over the lower or rather later in the alphabet numbers, and so they would be prioritized for lower numbers. Okay, but again, that's only if the numbering systems are the same numbers every time. All right, so there's still more steps. So each carbon-based substituent, those are also called alkyl groups, and you saw that on the last slide, but I'll just make sure that's really clear. Carbon-based substituents are called alkyl groups, get named after the number of carbons it has, so those same prefixes we looked at before, but you replace the ending with YL as opposed to ANE that we were looking at earlier. And any halogen-based substituent will have an O ending, chloro, bromo, etc. So substituents get listed in alphabetical order with the number of the carbon that they are bonded to in front, separated with this little dash, and that's a lot of words, so I'll make sure to go over this example we've been looking at with you. Okay, and if there are two or more of the same substituent, we use prefixes again. Now, what's annoying is that these prefixes are slightly different than the prefixes for the chains before. So 2 is di, 3 is tri, 4 is tetra, 5 is penta. You're not really going to see anything higher than that. All right, and the other key here is that the prefixes do not count towards alphabetizing the substituents in our name. And again, I'm going to go over all this with plenty of examples, so just stick with me. So we decided previously that this blue numbering system starting on the left gave our substituents the lowest possible combination of numbers. Then I have to look at, well, what are these groups hanging off of my main chain? These are both CH3 groups. And if you look back at the prefixes, any carbon groups that only have one carbon hanging off them start with the prefix meth. And so in this case, because it's substituents, it'll end with a YL. So these will be called methyl groups, both of them, because they're both one carbon. So because I have two of the same substituent, I also need to use a prefix, and in this case there's two of them, so my prefix will be di. All right, so let's get back to this step 6 here because there's a lot going on there. So the way that I would number and name this completely is I'm going to start with the numbers of the substituent carbons. So that's 2 and 3, and because they're the same substituent, I'm going to do 2, 3. That shows me where my two substituents are. Then I pull in this dash. All right, then to name the substituents, I'm going to put di because there's two of them, di. The substituent name is methyl, so that would be methyl. And then finally, the longest chain goes at the end of my name, which is pentane. All right, so those are all the different components of my name. So I'll break it down really quickly. First, you're going to have the number of the carbons that the substituents are on. Then you're going to have the substituent names, and if there's different types, they're going to go in alpha order, not including the prefixes. But in this case, there was only one type. And then finally, you're going to have your parent chain name. All right, so let's do some more practice for sure. Okay, so we're going to do practice with this molecule here specifically, but in case you're feeling overwhelmed by a bunch of words, here's a summary of what we're looking at. Okay, so first, find the longest chain, right? Make sure you don't fall into the horizontal line trap. If there's two longest chains, you're going to pick the one with the most substituents, okay? From there, you're going to number for the lowest possible number combo of substituents. So really, this should say number for the lowest possible. Sorry, typos. Not starting over at this point. Okay, if you can have multiple possible combinations of numbers that are equal, right? It's 2, 3, 3, no matter what, right? If all things are equal, then the halogens are going to get higher priority, meaning lower numbers over carbon groups. If it is still equal, then the alphabetical order is going to determine. So if it's earlier in the alphabet, ABC, it has a higher priority and therefore gets a lower number. Okay, then you're going to name your substituents, determine if you need any prefixes, and then from there you're going to assemble your name in alphabetical order, not including any prefixes that you might have added. So let's start with this molecule here on the right. So I'm going to look for the longest possible chain. I see one here, 1, This is 1, 2, 3, 4, 5, 6 carbons. But I also see a big substituent up here. So let me just check and make sure that that one's not longer. 1, 2, 3, 4, 5, 6 carbons again. Okay, so then all things being equal, chain with the most substituents. This horizontal one here has 1, 2, 3 substituents. If I work this way, this also has 1, 2, 3 substituents. So all things being said, it doesn't actually matter. So I'm going to pick the horizontal one as my main chain just because it's a little bit easier to see. So I'm going to first try a numbering system from the left-hand side to see what numbers it gives me for those substituents. All right, so this is the numbers that I get. My substituents are on carbons 3, 4, and 5. Let me try numbering from the right-hand side to see if it makes any impact on my substituent numbers. In the blue system, my numbers are 2, 3, and 4. So that would make the blue system correct for numbering this parent chain because it gives my substituent groups lower overall combined numbers. So now I need to name and figure out what's going on with these substituents. So I'm just going to pull up my prefixes to help me out here. Okay, and it helps me to circle my substituents, right? So here's 1, here's 2, here's 3. Now in this substituent furthest left, I have 1, 2 carbons. I do not count the carbon in the chain, right? That carbon's part of the parent chain, so it does not count as part of the substituent as well. I can't double count the carbon. So 2 carbons, my prefix is ETH, and because it's a carbon substituent, it ends in YL, so ethyl. Okay. As I work my way over here, I've got 1 carbon. Okay, so that's MET, and then YL, so methyl. And then here, also 1 carbon, so that's also a methyl. So alarm bells go off in my brain. I have 2 methyl groups. I'm going to need to also put a prefix in front of those substituents in order to make sure I can tell the reader that I have 2 of them. All right, so then I assemble my name. My substituents go in alphabetical order, not including any prefixes. Okay, so right now, I'm just going to make a list of my 2 substituents. I've got an ethyl group, and then I have 2 methyl groups, which means dimethyl. And then just to help me out, I'm going to make a list of what carbons those are on based on the blue numbering system, because that's correct. So it's 4 ethyl, and the 2 numbered carbons that the methyl group's on are 2, 3. All right, so now I need to put those in numerical order to assemble my name, not including prefixes. So it's E versus M, essentially, because I do not include the prefix in my alphabetizing. So 4-ethyl will come first in this name. So to assemble my final name, I'm going to do 4-ethyl. When I have 2 substituents, I get another dash. Then I get 2, 3 dimethyl. And with my last substituent, I do not put this dash here because I'm just going to connect it to the name of the parent chain. My parent chain has 6 carbons. Prefix for 6 is H, so that's going to be hexane. So that would be the final name for this example. Let's do a couple more quick examples before we end this video. So 2 more for practice, and this one looks kind of sneaky because it is written in our condensed format instead of in a line bond, which is the type we've been looking at. So I'm again going to just try to find and highlight the longest chain. So I'm going to assume it starts over here, working my way over, not going to go down here because that would end the chain pretty early. Keep going. Now I need to know, is it going to be longer if I head down here or longer if I just go straight across? This is 2 carbons, this is 3. So in this case, this is my parent chain. Let me just figure out how many carbons that is. First things first. 1, 2, 3, 4, 5, 6, 7, 8. All right, now I have to number the other way to see if it gives me lower priority substituent numbers. So 1, 2, 3, 4, 5, 6, 7, 8. So my substituents can either be coming off of carbon 6 and carbon 4 or carbon 3 and carbon 5. And so that makes the black numbering system correct in this case. Now let's go into naming my substituents. I've got a CH3 substituent here. If I want to pull up my prefixes again, I can. A 1 carbon substituent like this is called a methyl group. And then I've got a 2 carbon substituent here, which would be called an ethyl group. I only have those two substituents. There's no duplicates, so I don't need any prefixes in front of my substituent names. Alpha order, so ethyl's going to come first. Ethyl is on carbon 5, so my name starts with 5-ethyl, then another dash because I have another substituent to list, 3-methyl, and then because that's my last substituent, no dash at the end there, I'm just going to attach it to the name of the parent chain, which starts with oct and ends in ane. So 5-ethyl, 3-methyl octane is how we would say that out loud. All right, next one. I've got halogen substituents in this one, first example with that. So let me try to start highlighting my parent chain. I'm again going to start here and sort of work my way across, and then I need to stop. Is it going to be longer if I keep going left to right, which would give me 2 more carbons, or do I need to dip down 1, 2, 3? So I do actually need to dip down here to make my parent chain because that makes a longer chain. So let's figure out which way do I need to number this chain. I can go this way, 1, 2, 3, 4, 5, 6, 7, 8. Or I could go starting at the bottom, 1, 2, 3, 4, 5, 6, 7, 8. So my possible combos of numbers are with the blue numbering system. I would have 2 and a 2 here because, right, there's 2 substituents there, and then a 5, so 2 plus 2 plus 5, basically if you want to add it and get technical, but sometimes visually it's just easier, or I can have 4 and then 7 and 7, which is clearly much higher than 2, 2, and 5, and so in this case the blue numbering system is going to be the correct system. Let's look at what substituents I have here. So I have halogens for the first time, and I have 2 of them. So halogens are substituents end in O, so that's going to be chloro. And because there's 2, I need to put the substituent prefix on it, so it's going to be dichloro. Right? And then over here, I have a 2-carbon substituent. Again, I cannot count this carbon because that's part of the parent chain. 2 carbons, my prefix is F, and then I end it in YL. All right, alpha order not including prefixes. So C versus E. Okay, C is going to come first. So in my name, I need my 2 numbers where my chlorines are, 2, 2, and I do need to put it twice because if I don't put it twice, I'm telling the reader that the other chlorine could be on any of these carbons. I'm not being specific enough. So 2, 2, dichloro, then there's another substituent I need to name, so I put a dash. Blue is correct, so 5-ethyl. And then again, I have an 8-carbon parent chain, so it's again going to end in octane. So we'll do a bunch of practice with this, but hopefully this clarified and solidified a lot of those rules. It really just is about practicing applying the rules since every molecule has nuances that can make them slightly different. So we'll make sure to get more practice in as we go along.